Every single time you use the internet, open an app, or tap into a cloud service, you're actually witnessing this silent, incredibly complex conversation. We're talking hundreds, maybe thousands of computers all talking to each other. But how? How do they possibly coordinate when there's no single brain in charge of the whole operation? Well, this is the invisible dance of distributed communication, and we're about to break down the steps. And that, right there, is the fundamental challenge of what we call distributed systems. See, unlike a single computer that has one central memory and a master clock that everyone syncs to, these systems are just a collection of totally independent minds. So how on earth do they agree on anything, or even just have a coherent conversation? The answer, at first, sounds almost too simple. They talk to each other by sending messages, they pass notes. But as we're about to find out, that simple act, passing a note across a network, that's where all the complexity and, frankly, all the genius of modern computing really begins. Okay, so let's put a formal name to this whole thing: distributed communication. It's simply the exchange of information between processes on different machines, all happening through some kind of shared communication channel. Really, you can think of it as the nervous system of the entire internet. So if computers are passing messages back and forth, how are they actually doing it? Well, it turns out there are two fundamental philosophies, two really different ways to structure the conversation. On one side, you've got synchronous communication. The best way to think of this is like a live phone call. And on the other side, there's asynchronous, which is much more like sending a text message. The key difference really comes down to a few key ideas. Is the conversation blocking? Does it require a rendezvous? Or does it use a buffer? Let's break that down. Okay, so in synchronous communication, when a sender sends a message, it just stops, it blocks. It won't do anything else until the receiver comes back and says, "Yup, got it." Both computers have to be ready at the exact same moment for this exchange to happen. That's the rendezvous. It's like a planned meeting. It's very predictable for sure, but it can also be kind of inefficient. Asynchronous, on the other hand, is what you might call the send and forget model. The sender just fires off a message and immediately moves on to its next job. It doesn't wait around. The message just sits in a buffer. Think of it like a digital mailbox or a queue, waiting for the receiver to come and pick it up whenever it's ready. This is way more flexible and, honestly, how most of the internet works. Now, that flexibility we just talked about with asynchronous communication is super powerful, but it introduces a whole new problem. What happens if one computer in the conversation is a much, much faster talker than the other one? Imagine trying to pour a gallon of water into a tiny little funnel all at once. It's going to overflow, right? You'll lose most of the water. Well, the exact same thing happens here. If a huge, powerful server sends data way too quickly to, say, an older smartphone, that phone's buffer is going to overflow and data will just get lost. The whole system becomes unreliable. The solution to this mess is called flow control. It's basically a set of rules that acts like a valve on that funnel, making sure the sender slows down to match the receiver's pace. It's all about preventing that overflow and keeping the conversation running smoothly and efficiently. The absolute simplest form of flow control is a protocol called stop and wait. You can think of it as a very polite, but very, very slow conversation. The sender says one thing, then it just stops and waits for the receiver to send back an ACK, which is just short for acknowledgement. Only after it gets that ACK can it send the next piece of information. It's simple, yeah, but you can imagine how painfully slow this gets over long distances. Okay, so we've figured out how to manage the speed of the conversation. But what about the content? Does the order in which messages show up actually matter? The answer is absolutely. It's critical. So, check this out. Imagine a computer sends two really important commands. The first message, M1, says, "Lock this important file so no one else can edit it." And the second message, M2, says, "Okay, I'm done. Go ahead and unlock the file." The order here is everything. So what happens if the network has a little hiccup and it delivers the unlock message before the lock message? Well, the system would try to unlock a resource that was never locked. Then it would lock it and maybe never unlock it again. The result is just total chaos, inconsistency, and a completely broken system. The guarantee we need here is called FIFO, or first in, first out. It's a simple promise. Messages will be delivered in the exact same order they were sent. That's it. This is the bedrock of logical consistency. It's the reason your chat messages appear in the right sequence and not as some jumbled, confusing mess.
Now, FIFO is actually just one piece of a bigger puzzle called quality of service, or QoS. Think of QoS as a kind of contract for the communication channel. Different applications need different terms in that contract. Video streaming, for example, needs low delay to avoid buffering, but it can handle losing a few pixels here and there. A banking transaction, though, it demands perfect reliability and ordering, no excuses, even if it takes a fraction of a second longer.
So we've got rules for speed, and we've got rules for order, but we're building all of this on top of a physical network that is, by its very nature, chaotic and unreliable. So what happens when things just break?
I mean, messages can get lost in transit, just vanish into thin air. They can be accidentally duplicated by a network hiccup, the data inside them can get corrupted like a smudged word on a page, or entire sections of the network can get cut off from each other. This is the messy reality our communication protocols have to deal with every single second of every day. To fight all this chaos, engineers have developed this amazing reliability toolkit. Acknowledgements, or ACKs, confirm a message was successfully received. If an ACK doesn't arrive within a certain time, that's a timeout. The sender assumes the message was lost and just retransmits it. And to handle all those retransmissions, every single message gets a unique sequence number, so the receiver can spot and just throw away any duplicates. It's this beautiful dance of mechanisms that creates the illusion of a perfect, reliable connection over a totally imperfect network.
So when you really pull it all together, what you see is that our entire digital world, from our chats to our banking systems, is built on a foundation that is fundamentally unreliable. It's made dependable not through perfect hardware, but through layers and layers of these incredibly clever rules. It really makes you wonder, right? What is the true nature of trust in a world that is built from the ground up to expect and to overcome constant failure?